Okay, guys, here's a recording to go ahead and finish off this chapter. If you remember last time, we were talking about limiting reactants. And the limiting reactant is what will run out first. And so we had this scenario where we had this reaction, right? And the reaction said that we would get, or we would react 1 mole of Fe2O3 with 2 moles of Al to get 1 mole of Al2O3 and 2 moles of Fe. So asking which is going to be the limiting reactant, we go through this process of looking at the same product, right? So we look at Fe and we find out that indeed the limiting reactant is aluminum, right? So if we can produce this, we would produce potentially 4 moles of Fe. Then we can also go back and say, okay, if we did use those 4 moles of Fe in the reaction, how many moles of Fe2O3 were used? And there are only 2 moles, right? And we started out with 3. So again, we would have a leftover, or we would have excess of 1 mole. Okay, so that was with moles, right? And when you have moles, you can compare those using that stoichiometric ratio. But when you have grams, you first must take it to moles, right? And so here in this equation, we've got 8.25 grams of the S8. We have to take that to moles first. Once we get to moles, we can use the mole ratio. Once we use the mole ratio, we use the grams of chlorine, right, to find out how much chlorine is going to be used. Okay, so now we could go. We know that we have 17.4 grams of chlorine, and we're only going to use 9.12, and so in this case, the limiting reactant is the S8. Now that's a different way to show it, right? Because you took this 9.12 grams, or you took it back to grams of the reactant. Now down here in the bottom is where we're actually doing it the way we did it in the previous slide, where we take the S8 first, right? We convert that to moles. We use the mole ratio. We go back to S2Cl2, right? And then we get grams of S2Cl2 that we could make from S8. We already know that S8 is the limiting reactant, but if we were to do this the way we had done it in the previous slide, we would now do the same thing with chlorine, Cl2, find out how many moles, do the mole ratio, find out how many grams, and it would be more grams than 17.4, right? Okay, so the next step in this process now is to look at percent yield. So percent yield is actually, you have to be given the amount, right, that was produced in some way, right? And so in this case, we're saying, look, what if we only produced or formed 15.4 grams of that S2Cl2 from that previous reaction, right, that previous page where we found the limiting reactant, we would say, okay, we could have gotten 17.4 if we take the 15.4 that we got, the actual, over the 17.4 that was theoretical, and multiply that by 100, we get 88.5%. Okay? All right. So then we can kind of continue this thought and say, you know, we've got these historical yields in these reactions, and it says if we know the reaction from sulfur to chlorine has an 88.5% yield, how much sulfur will we need to produce 500 grams of S2Cl2, right? And so when we start to solve this, we first go with this idea that we need 500 grams, right? But we know that there's only an 88.5% yield, And so if we look at this equation, we set 500 grams equal to, right, because 500 grams is the product formed, right? And then we've got to find the mass predicted by stoichiometry. And so from the equation down here, we get 565 grams. We now plug that in to this equation, right, where we're looking at 565 grams. We convert that to moles. We take moles of S2Cl2 to moles of S8. We find out the moles of S8, and we eventually get back to grams of S8. So this says that if you start with 268 grams of S8 and you have the typical yield of 88.5%, then you will get out 500 grams of S2Cl2. So let's talk about titrations, right? And in a titration, we know that we can use this M1V1 equals M2V2. In this case, we're saying MAVA, or molarity of acid, volume of acid. Molarity of base, volume of base. Okay. If you ask the question, what's the concentration of sodium hydroxide, NaOH, if it requires 23.7 milliliters of NaOH to titrate 42.8 milliliters of 2.6 or 0.263 molar HCl. Well, now we've got a concentration of HCl, and we've got a concentration here, and we've got a volume right here, and so we can multiply that 0.263 right by the volume will get us moles, and then divide by the volume of the solution, right? The base, the volume of the base solution, and we'll get a molarity of 0.475. That's a titration. To get to the end point, right, it takes 23.7 milliliters of NaOH to get to the end point. There are a lot of other titration methods. This is not that much different than what we just looked at, but if you want to look at the iron content, there's a reaction with potassium permanganate where you can get potassium permanganate reacting with Fe2 plus, and you put some acid in there, and you will convert the Fe2 plus to Fe3 plus, and the Mn, let's see, the MnO4 is in the +7, it goes to the +2, and so we look at the stoichiometry of this, and the stoichiometry of it is 5 to 1, right? And so we can plug in the stoichiometry of 5 to 1 here, and we can find the number of moles from the molarity of the MnO4, the original amount of MnO4, and then we can use the molar mass of iron to find out how many milligrams of iron there are in that sample. We'll talk a little bit about combustion analysis, and sorry this slide is a little messed up, but in combustion analysis, what you have is you have a sample that's put into an oven. You pump in some O2, right, because that's the combustion, and then what you get out in combustion is H2O and CO2, right? What you can then do is you can back calculate from saying, okay, how much H2O did I get? In terms of grams, I can convert that to moles. I can find out how many moles of CO2 I got from grams to moles. Now, if this thing just contained hydrogen and carbon, now I know, right? Now I know how many moles of hydrogen, how many moles of carbon. Just you have to use the mole ratio of 2 to 1 with hydrogen to water, and the 1 to 1 with carbon to carbon dioxide. I've got moles of carbon, I've got moles of hydrogen. I can go back to, I've got moles of each of those. I can go to the lowest whole number ratio by dividing by the smallest number of moles and get an empirical formula.